So here is homework number, what are we on? Number 16 already. Okay. And this is problem 1, and here's a video solution. We have this crank slider. So it's cranking here and it's sliding there, thus a crank slider, and has a angular velocity of 10 radians per second. That should have been omega AB, or that should have been omega A, one of those should match. And an angular acceleration of 2 radians per second squared, and they're both going clockwise here. This length is 75 millimeters, and this is 225 millimeters. The crank at this instance is at 60 degrees. The connecting rod is at 45 degrees, and this piston is traveling on a slope of 15 degrees. And we want to find the velocity and acceleration of the piston. So that's sort of a typical problem. So here I have it written out in a nice, neat format. And let's see. I have to figure out where I started with this. Started somewhere here. Interesting. Why did I do it this way? I'm just looking at my velocity. I'm looking at what I've written down here. And okay, yes, I see what's going on. Okay, so I had the wrong thing marked as page 1. So there's page 2. So I could start the video again, but yeah, it's real life, right? Okay, so I start with what I know, which is going to be this stuff right here, and I do a velocity analysis of this. So I'll make a nice, neat little drawing of this piece right here, and I'll put a little center line onto there. And we know that it's going to have a velocity of this right here. So here's our velocity of B. It's going to be omega AB. This up here, times LAB. So that's going to be our, 10 times 75 millimeters, right? And so we're going to have 750 millimeters per second. So let's put some of this other stuff on here. Now, we are also, while we're here, we could also do the acceleration, find out what the accelerations are. So there's going to be an acceleration that's coming down right here. And there's also going to be an acceleration right here, right there. So I'll write out this one first. That's going to be the acceleration of B with respect to A in the tangential direction. And that's going to be alpha AB times LAB. And alpha, we're told, is 2 radians per second. All right, did I get that right? Yep. And then 75 millimeters. So 150 millimeters per second squared. We're also going to be, so that's associated with that one. Then we have this guy right here. He's going to be the acceleration of B with respect to A in the normal direction, or omega AB squared LAB. And so that comes out to 10 squared times 75. So we have 7,500 millimeters per second squared. Now I'm going to take a look and see. A lot of times it will be in our best interest. No, I think in this one we're going to be okay by keeping it in the normal and tangential. Sometimes it's best to turn this into an X and a Y right here. It just makes it a little simpler to think about and keep track of. But I didn't do that in this case. But in some of the other problems, I will. So just be aware. Sometimes it's a little easier here. We might want to just take a note right here of which angles we're talking about. In this case, because this is 60 right here, that would be 60 right here. So this is 30 degrees, and that's 30 degrees right there. And some people will like write this out over to the side of what angle and so forth, and do that method. It's pretty good to keep track of it that way. Now, I did the velocity analysis in two separate ways on mine, but I think I'm going to go ahead and just do it in a single way. Right, thank you. I don't want to see my security report. I'm going to do it with ICR, do my velocity analysis of this link, BC. And I'm going to make a good drawing of the thing down here. It's at a 45-degree angle, so I could actually use my grid to try to get a better 45 right in there, right? And that's a pretty good 45. Now, I'm going to try to get a decent looking 30 degrees, right? So that's the velocity right there we have of 30 degrees. So, let me see if I can do a decent job up here. Now, I think I'm not going to have enough paper for making this accurate here. So I'm going to do a little bit more than 30 degrees just so I can, yeah, even still, I'm going to have to make this smaller to be able to use this paper effectively. All right, so I'll make my approximate 30 degrees here. And then I'll make my value here coming up. Even then, no, see, that's too close. I need to make it, damn. Should probably do this in CAD, huh? There you go. All right, so I've exaggerated this a bit, just so that I could get it to fit onto the paper. Let's see. All right, even still, I'm going to have a little bit of a problem here because I want to have my 15 coming like that. So I made that very, very narrow. It's like I exaggerated that so it wasn't 15 because I want these two to connect. So if this was accurate, it would be like way up in there, right? So I'm going to cheat ever so slightly here. And so here's my ICR right up here. And so these angles right here, okay, so this angle right there is, let's see what I decide. Okay, so this angle right here is 15. This right here is 75. And this right here is 45. So if I do that, 75 and 45, put those in there. Let's see, I'll even write it out here. 45 and 75, which I need a calculator for, is 120. Therefore, this is 60 degrees, right? Let me label this. This is V C right here, right? And so this is VB. Now, this angle right here is, well, this angle, okay, I'll take it back. This angle right here is 45, right? This angle here is actually the extension of my crank, so it's 60 degrees right there. So I have 105 degrees here and 60 degrees there, and what ends up happening is that this is 15 degrees. So I see that the velocity that I know, and I'll make it a little darker. The velocity that I know is VB, so we're going to have an angular velocity of omega BC. That's going to be right here. And my RB with respect to ICR is right here. And my RC with respect to ICR is right there. And I can find my, from law of sines, and I know this length right here is 225 millimeters. So I could take the law of sines and say that my RB with respect to ICR divided by the angle that's opposite from it, which is 60, it's going to be equal to my 225 divided by the sine of 15. Looks like my wife is home. All right. So I plug those numbers in and I get 752.9 millimeters. Okay. While I'm at this, I should also get my RC with respect to ICR. And that's going to be the sine of 105 equal to 225 over the sine of 15. And I get my RC with respect to ICR to be equal to 839.7 millimeters. So knowing that VB is equal to omega BC times RB with respect to ICR, we can find omega BC is equal to VB over RB with respect to ICR. So that's, which one is that? 750 up above, divided by my 752.9. So omega BC, getting sloppy here at the end. This is going to be a long assignment, so need to be nice and neat. That omega BC turns out to be 0.9962 radians per second, and it's counterclockwise. And then we can also get the velocity of C is just the omega BC times R C with respect to ICR. So we get 0.9962 times our 839.7, and we get 800, well, very close to 836.5 millimeters per second. What's going on here? Thank you for that notification there. Okay, so we've got, at least we got the velocity of this. We used ICR for it. We could also use the 3-diagram method. We could also use vector math. We have lots of options. All right, so continuing on. This is page 2, and I'll fill out the rest of this stuff later. And now we want to get the acceleration analysis of link BC. And I should actually just start right down here. Link AB, and then ICR of link, I'm trying to write these things out here, BC, and then acceleration analysis of link BC. Now, a careful sketch is really going to help assist in this. This thing is at 45 degrees, right? So we can kind of use our grid to get us a pretty decent 45 degree in there, and looking for, there you go. And then the last one over here. Where'd you go? There you go. Okay. Don't look too terribly bad. Well, I'll start at the same spot, so this should be all the same length, right? Okay. So what we know we know up here we have, we'll draw the X and Y axes just a little bit there. We know that we have on here 30 degrees downwards, so I'll try to make that look right. About 30 degrees right here, and we have perpendicular to that. So this is going, this was, remember, this was our tangential right here. That's the tangential one of 150, and then this one is our normal of 7,500. So could write it out a couple different ways. What did I decide to do? Did I label it? I did, but I think I'm gonna write put in what the values are. So first off, I want to say that's up 30 degrees right here, and I'll say this is 30 degrees, and this is going to be the acceleration of B with respect to A in the tangential direction, and this is the acceleration of B with respect to A in the normal direction. Okay. And this one right here is going to be steeper, or let me, like that right there. This is the acceleration of C, and that's 15 degrees. And I'm guessing that direction, by the way. So I'm guessing that it's going to be going downwards that way. So I'm going to put them both. I'm going to put the thing I know at both places right here, and that's this right in here. All right, so I'm going to repeat it. Here's my 30 degrees. 30 degrees right there. And this is the, did I put numbers down there? I think it did. I think, and this is the spot where I put, decided to put that it's going to be 150 millimeters per second squared, and acceleration of B with respect to A in the normal direction is 7,500 millimeters per second squared. Put that on there. Now, because technically speaking, it's maybe good to also put it up into there, right there. We don't have to write everything out onto this one. Whoop, I don't mean that angle. I mean that angle. Okay. And acceleration of B with respect to A. Tangential acceleration of B with respect to A, and normal. Now we're going to pin it right here at that spot, and we know that it's going counterclockwise. Here is omega BC. That's going to create a normal acceleration that we can find, right? And so I wrote that out. Acceleration of C with respect to B, which is omega BC squared LBC, right? And I'd like to put that the value of that in there, although it will be kind of squeezing some stuff in. 0.9962 squared and 225. So we say that is 223.3 millimeters per second squared. Now this is 45 right here, so this too is 45 right here. And I'm going to go ahead and guess my alpha BC is going to go counterclockwise, and therefore I'm guessing my acceleration of C with respect to B in the tangential is going to be in that direction. And that is going to be alpha BC times LBC, which is alpha BC times 225. And if this was some other angle, we would be doing the same thing. So let's go ahead and put this in here. This is our 45 degrees, and here is my 45 degrees. Woof, that's a lot, but it's going to help us keep track of everything. So we're writing an equation for this. So our main equation that we're writing this whole thing for these are all vectors. So, and recognize that this is the acceleration of B, and maybe it would have been better if I broke it down into X and Y, and I will in the other two problems. This one, I kept them. I kept them the way that they came off of the first link. But let's see. I'll go for the X direction first. Sometimes there would be some advantage to picking one, but we're going to end up with two equations and two unknowns. The two unknowns are going to be alpha and the magnitude here. So remember when we're doing this, we're basing it on the diagram on the directions. So this one right here is going to be AC times the cosine of 15 degrees, and it's positive. Here we're going to have, there's going to be several different things here. But let me start with this. We know that this is negative, right? This is then the negative X direction. So we have a negative 7,500, and that's going to be times the sine of 30. And then here we're going to have a positive 150 times the cosine of 30. Here from this, well, let's go to, we wrote this one first, so we'll put it in here. We're going to have a positive alpha BC times 225, but that's going to be the way that I've written the angles here, sine of 45, but we're not done. Got to remember that we have this component right here, so we have a negative 223.3, and that's going to be the cosine of 45. And I'm going to go ahead and simplify this all down so that I get the acceleration of C is going to be equal to, it turns out to be negative 3,911 plus 164.7 omega, excuse me, not omega, but alpha BC. So that's the first equation, and I expect to have a second one. So in the Y direction, go back up to this diagram, looking right here, and I have a negative AC sine of 15 right here. Come back over to here, and I have a negative 7,500 cosine of 30. And by the way, notice when you're doing these, you'll notice there's a sine here, there's a cosine there, and that kind of thing. It's just a double check that you didn't go too quickly and look over something. This one is also negative, and that's going to be the sine of 30. Now let's go to the tangential one, because we wrote that one here, and that's going to be positive alpha BC times 225, and now this one is going to be the cosine of 45, and I have to once ahead again have to come back to the next line, and this is positive, this one, right? So there's a positive 223.3, and that's the opposite from the angle, so that's a sine 45. And I can collect all this stuff, AC is now, okay, so I collected all the constants and put them together and then divided through by a negative sign of 15 on here, and I got 24,000, it was positive 775 minus 614.7 alpha BC. That's going to be my second equation. I equate 1 and 2, and I did this. Well, go ahead, I'll write it down. Why not? Negative 3,911 plus 164.7 alpha BC is equal to 24,775 minus 614.7 alpha BC. Therefore, I can get alpha BC is going to be equal to 36.81, and it's positive. Therefore, I knew that it was counterclockwise. I guessed correctly, and now I can plug this back into, well, I can put it back into either of them and come up with my answer. So that came up to 2,151 millimeters per second squared. And so my answers are velocity of C is equal to, and where did you go? 837 millimeters per second squared at 15 degrees downwards, and the acceleration is 2,151 millimeters per second squared, 15 degrees downwards. Long problems. A lot of opportunities to make mistakes, but this type of problem right here helps you develop these skills to work through a complex thing step by step, breaking it apart. Teaches you tenacity. There's all kinds of benefits that will translate into future success in engineering.